Hello, my name is Xiaolin Li. I'm a second-year undergraduate student at the University of California, Santa Cruz. I'm going to talk about our comparison project on measuring the surface energies of Titan's Haze analogs, Tholin. The background image here is a near-infrared image that penetrates through the haze layers, revealing Titan's hydrocarbon lakes of its north pole, and its specular reflection can be seen very clearly. Let's talk a bit more about Titan's haze layers that gives Titan the orange color. Titan's atmosphere is composed mainly of nitrogen and methane, with small amounts of hydrogen, carbon monoxide, and argon. Titan's surface temperature is around 94 kelvins, and it has a surface pressure 1.5 times of Earth's surface pressure. This combination is very close to the triple point for methane, so both liquid and gaseous methane can exist on the surface of Titan. Titan's atmosphere will form complex organic haze particles after interacting with the energetic particles from a variety of different energy sources. These energy sources can either be Saturn's magnetosphere or UV rays from the sun. These complex solid organics then form Titan's thick haze layers. They can become potential cloud seeds in the atmosphere, or they eventually fall down to the surface and have the potential to form the organic dunes that Cassini has observed, or interact with the hydrocarbon lakes. Knowing the surface energy of the hazes can help us understand both the cloud formation processes and the haze's interaction with the surface liquids. Unfortunately, we don't have a sample of the haze from Titan, so we have to use laboratory analog. We produced the analog material Tholin here on Earth under Titan's atmospheric conditions. There are many production methods, but most production methods look something like this. A gas mixture that mimics Titan's atmosphere will flow through a temperature control to simulate the temperature of Titan. A mass flow controller will control how much gas goes into the reaction chamber where they're exposed to the energy source. Here we use two main types of energy sources, UV lamp which mimics solar UV radiation, and cold plasma which mimics energetic particles from Saturn's magnetosphere. We're using one type of UV lamp and two types of cold plasma sources, the alternate current cold plasma and the PDN, which stands for the pulse discharge nozzle. New particles are then formed and deposited onto a substrate, and a Tholin film is formed. All Tholin samples used in this project are stored in a vacuum desiccator prior to measurements to avoid the contact with oxygen and moisture in the air. For our study, we used 5 different samples produced in different laboratories under different experimental conditions. I have listed their respective energy source, gas exposure time, pressure, gas flow rate, and temperature here. The two energy sources used to produce the samples are UV radiation and cold plasma discharge. 4 of our samples will be from gas mixture of 95% nitrogen and 5% methane, and the other will be 94.5% nitrogen, 5% methane, and 0.5% acetylene. We're using a variety of samples because each lab produced Tholin under different experimental conditions and have different setups. There are too many variables, and even a small change to one of these variables could cause Tholin to have different properties. The properties of Tholin produced by Johns Hopkins University has been measured before by you et al., but the solid Tholin produced with these different laboratory setups have never been cross-compared before. For our study, we focus on one important bulk material property of Tholin, the surface energy. Surface energy is the free energy change when the surface area of a medium is increased by unit area. In other words, it's the energy needed to create a new surface or break one surface into two. It's usually denoted by gamma. It's an important property of any material because it determines how adhesive and wettable it is, therefore affecting the interactions between different materials. Material with high surface energy, usually polar, suggests that they are easy to adhere to and easy to bond with. They also have good wettability to liquids, meaning liquid will spread out on the solid surface. Material with lower surface energy, usually nonpolar, suggests that they are hard to adhere to and have low wettability to liquids. Additionally, surface energy could also inform on the bulk chemical composition of the material, which is very useful for comparing these different Tholin samples, as they are complex organic mixtures that are hard to compare with chemical analysis. We'll be measuring surface energy via the Cecil drop contact angle measurements. The relationship between surface energy, surface tension, and contact angle can be described by the Young-Dupre equation, shown in the yellow box here. The measurements are conducted in dry nitrogen to avoid vapor absorption on the surface and contamination from oxygen. More specifically, videos of liquids are taken using an oscillogoniometer. Here's a sample image displaying liquid droplet on a Tholin film. We'll be using a total of 2 different liquids, diautomethane, which is a nonpolar liquid, and water, which is a polar liquid. We are using Oscilla's contact angle measuring software to get our contact angles. Oscilla software uses a box for phase definition and an edge detection algorithm to find the drop edge and measure the angle. It uses a polynomial fit for angles that are 10 degrees and above, and a circle/ellipse fit for angles that are 10 degrees and below. Sample result we get looks something like this. Here are the contact angles between the test liquids and our Tholin samples. Using the Young-Dupre equation shown in the previous slide, the total surface energy can be calculated. The surface energy can be divided into dispersive and polar components, which tells us the bulk chemical composition of the sample. The samples have a diverse range of surface energies, ranging from about 45 to 75 millijoules per meter square, but in general are relatively high. Our Johns Hopkins University samples are produced under the exact same experimental condition other than their energy source. However, the 2 samples have quite different surface energies. UV Tholin has a smaller polar component compared to plasma Tholin, even though their dispersive component is similar. This can be caused by the fact that UV rays can't dissociate nitrogen directly. Nitrogen is the main contributor to the polar components of the molecule, so not being able to dissociate them lowers the polar component to surface energy. Although UV light cannot directly dissociate nitrogen, there are other ways to incorporate them, so that's why there is still a polar component to the UV Tholin sample. For our 2 cold plasma Tholin samples from NASA Ames, their exposure time to the energy source is much shorter than our Johns Hopkins University sample. Such a short exposure time can cease the formation of more complex molecules. So acetylene is added to one of the samples as a precursor, so even in such a short exposure time, complex molecules can still form. From the surface energy, the Tholin sample with acetylene in their gas mixture has a higher surface energy. This may indicate that larger and more complex molecules are formed with acetylene being in the gas mixture. Despite their short exposure time, the surface energy of the Tholin samples from NASA Ames have a similar total surface energy to the UV Tholin from the Johns Hopkins University sample. This can be due to the higher pressure, gas flow rate, and temperature. Our sample from University of Northern Iowa has a similar surface energy as the UV Tholin from the Johns Hopkins University sample. Even their dispersive and polar components are similar as well. This can be due to having a common energy source, the UV lamp. Even though the University of Northern Iowa sample has a longer gas exposure time, higher reacting pressure, and temperature than the Johns Hopkins University sample, both were created under a UV lamp, so both of them can't dissociate nitrogen, and therefore yielding a similar product. Now we have the surface energy of Tholin. What can this mean? Haze particles that remain in Titan's atmosphere can become cloud seeds, or cloud condensation nuclei. The requirement for a good cloud seed is that a material needs to be soluble in the possible hydrocarbon condensates, methane and ethane, or it makes a low contact angle with the hydrocarbon. We know that tholins are not soluble in these hydrocarbons, so we need to estimate the contact angle between tholin and the hydrocarbons. If our tholin samples are just like the haze particles on Titan, again using the Young-Dupre equation, the theoretical contact angle between the possible hydrocarbon condensates and tholin can be calculated. For methane, the theoretical contact angle is about 0 degrees, meaning that the haze particles will be a good cloud seed. For ethane, the theoretical contact angle ranges from 0 degrees to 40 degrees, meaning it can't possibly be a good cloud seed. The haze particles can also fall onto the surface of Titan, where they have the potential to interact with the hydrocarbon lakes. If they fall into the hydrocarbon lakes, they would either sink or float. The haze particles are likely denser than the hydrocarbon molecules of the lakes, but it can still float if the contact angle between the haze particles and hydrocarbon is greater than 90 degrees because of the capillary effect. However, if the contact angle is less than 90 degrees, the haze particles will sink. If tholin is just like the haze particles, then the contact angle formed with the lake liquids and all the tholin samples will be less than 10 degrees, suggesting that the haze particles will sink when they come in contact with the hydrocarbon lakes and become lake bed sediments. Here's a little short summary of my main conclusions and some possible future work. I'll leave my summary slide up here for any questions or comments. And that's my presentation, and thank you for your attention.